All right, New York number theory seminar today, September 14th. And what I'm going to do for various reasons, not least because I got a message from an editor at Springer telling me that I had promised them the third volume of my books on additive number theory, and it was due 10 years ago. So they said they would give me until January. I said, sure, no problem. So I'm actually going to go back in time and talk about some things that I talked about in the seminar here before some of you were born. So you probably haven't heard it before. And so this is additive number theory. And so the basic scheme is you have A is a set of integers, often non-negative. And we have an integer H, at least 2. And we look at the sum set denoted HA, which is all numbers that you can write as the sum of H elements of A and not necessarily distinct. And the so the direct problem is given A, describe HA. So many classical problems in number theory fit into this scheme. For example, if A is the set of squares, then to describe HA is to ask what numbers can be written as sums of H squares. And the archetypical theorem in the subject is Lagrange's theorem, which says that for this set A, for A is n naught. N naught is the non-negative integer. So the classical theorem that every number is a sum of 4 squares says that if you take the squares, the fourfold sums are A. And then you ask more refined questions. Well, in fact, 4 is the best you can do. If you take 3 squares, not every integer, not every positive integer is a sum of 3 squares. And you can ask what numbers are sums of 3 squares and what numbers are sums of 2 squares. If you ask what numbers are sums of 5, 6, or 7 squares, of course, it's every integer, because all you need is 4. But then people ask, well, okay, but how many ways can you write a number as a sum of H squares? And that's a whole vast subject in itself. If we take A to be the set of cubes, again, you can ask what numbers are sums of cubes. And there's a theorem which is due to, who's it due to? Wieferich, which said, let me call this A3, just indicate it's cubes. If you take 9 cubes, you get all integers. And 8 cubes don't suffice. So you can look at sums of cubes, and the more summands you're allowed, the more integers you get. And when you finally have 9 cubes, you get everything. But 8 sums of 8 cubes, this is not the set of integers, right? But it's a remarkable result due to Landau, that if you look at all the non-negative integers, which are not the sum of 8 cubes, there are only 2 of them, 23 and 239. So, so there's something, so the fact that every number is a sum of 9 cubes is a true statement, but somehow it misses what you might call the essential character of the cubes. You only need 8 cubes to represent all sufficiently large numbers, in fact, all but 2 numbers. So if you want to understand the cubes as what is called an additive basis, well, 9 is not the right number. The number is no bigger than 8. And in fact, this was actually sharpened in some sense by Linux, who proved if you look at sums of 7 cubes, the number of integers, the set of integers that are not sums of 7 cubes is a finite set. And they've also been enumerated. There are relatively few of them. So if you want to understand the character of the cubes, well, 7 cubes is the most that you need. And people would like to know how many cubes you really need to represent all numbers, all integers from some point on. And there's a simple congruence argument that says sums of 3 cubes won't be enough. If you take a sum of 3 cubes, you'll never get the congruence classes 4 or 5 mod 9. So, but maybe 4 cubes. And a nice open problem. This is in the category of problems that have been open so long. I don't know, they've just been open for a long time. What numbers are sums of just 4 cubes? Do you get all numbers from some point on? There's a density theorem of Davenport, I think, that if you look at the sums of 4 cubes, that set has density 1 in the integer. So almost every integer is a sum of 4 cubes, but the missing set has density 0, but sets of density 0 can be infinite. So this is really a nice question. So what this suggests is the following definition, which is the core of many results in additive number theory. So a set A, non-negative integers, is called an asymptotic basis of order H if the H-fold subset HA contains all but finitely many or all sufficiently large integers. So this is the basic thing we want to study. And so a slightly more quantitative way to say this is the following. Let's define the representation function. R sub AH of n. So this depends on a fixed set A of non-negative integers, and H is a fixed number of sum n's. And this is going to be equal to the number of ways you can write n as a sum of H elements of A. So it's the number of such representations. Now, there are different ways you can count representations. So, so the first way is just this. This is the same as saying this is the number of n tuples, H tuples, such that n is AI1 up to AIH. So in this definition of the representation function, if you have, for example, 2 and 3 in your set, then 2 plus 3 equals 5 is one representation, and 3 plus 2 equals 5 is a second representation. And another representation function which one can define, and it's really a matter of choice in most cases what one wants to use. You can look at the number of H tuples in H, where
but they are mini flowers.
N is the sum of these H elements of A, but these elements are in non-decreasing order. AI1 less than or equal to AI2 less than or equal to AI sub H. Okay. So in the case of this first representation function, there's a very simple generating function you can write down for it. If you let f sub a of z be the summation z to the a, where a just runs through the non-negative integers in the set A, then if you take f sub a to the h power, you get a power series and goes from 0 to infinity, c to the n, where the coefficient of z to the n is this representation function, r sub ah of n. So this is the representation function where the order of the summands matters.
You're running off the edge of the page to the right.
Oh, sorry.
That's good.
Okay. Okay. Now, since oops, let me just wish I could close this. Oh, there it goes. So I'm going to start with something that came up recently because David Chudnovsky asked me a question. He remembered that in one of the papers of Erdős and Turan, they use a theorem in complex variables called Fabry's gap theorem. Fabry's gap theorem. And this appears in one of the classic Erdős-Turan papers. It's a paper of Paul Erdős and Paul Turan, which appeared in the Journal of the London Math Society in 1941, volume 16, 1941. Very short paper. I think just 4 pages long, 3.5 pages long. 212 to 215. And in this paper, Erdős and Turan are interested in showing the impossibility of the representation function of a sequence of integers being too regular. And what they meant by too regular, like the simplest, most excessively regular form of a representation function, would be one that was constant, or let's say even eventually constant from some point on. And they proved this was impossible. And they proved it by using Fabry's gap theorem. So let me just show you the Erdős-Turan argument. So so let A be a set of non-negative integers such that R sub A H of n, so A is the set, H is the fixed number of summands, is equal to some constant K for all n greater than or equal to n naught. Right? They want to show this is impossible. Now, the first statement you can say in this case is So if A is a sequence that has this property, actually, let me just use, okay, no, that's fine. So let me state a little lemma. If R sub A of H of N is not necessarily constant, but certainly bounded for all N, then the density of A is 0. And by the density of A, we mean the following. So that A of X, just count the number of elements in the set A less than or equal to X. So this is the counting function of A. And the density of A, if it exists, is the limit of A of X over X as X goes to infinity. Now, so suppose this representation function is bounded. Suppose this representation function is not bounded. Suppose it's positive. So if the density of A is greater than 0, then lim sup, A of X over X, is some number lambda greater than 0. So you can choose large values of X with A of X over X greater than lambda, or A of X bigger than lambda X. So if you count the number of pairs, if you count the number of pairs AI, AJ, pairs of the terms of elements of A, with AI and AJ both less than or equal to X. So this is A of X squared. This is greater than or equal to lambda squared X squared. So then if you look at the sum of the number of representations of an integer, let me just restrict this to the case H equal 2, because that's all that Erdős and Turan considered in their paper. So we have a set of A of integers, and we're looking at representations of N as a sum of two terms from the set. So if the number of representations is bounded, then I claim that the density of the set is 0. So if the density is unbounded, then you have large values of X for which A of X is greater than lambda X. If you count the number of pairs of elements of the sequence where both terms in the pair are in most X, there are at least lambda squared X squared of them. And if you look at R sub A2 of N, and if you sum that for all N less than or equal to X, you're counting every one of these pairs exactly once, right? Because for each N less than or equal to 2X. Because if AI and AJ are both less than or equal to X, AI plus AJ is at most 2X. So if you're counting the number of representations of all integers N up to 2X, there are at most lambda squared X squared of them. Right. Which means what? So lambda...
At least lambda squared X squared, yeah?
Sorry?
At least lambda squared X.
Right, greater than or equal to lambda squared X squared. So lambda squared X is less than or equal to 1 over X, our summation, R sub A2 of N, N less than or equal to 2X. Let me divide this by 2. And so lambda squared over 2X is less than or equal to what? The average number of representations. But if the representation function is bounded above by C, this is less than or equal to C, right? Each of these numbers is in most C, which says that X is less than or equal to 2C over lambda squared, which is a contradiction because you can find arbitrarily large values of x, where a of x over x is at least this positive number lambda. So if you have a set of integers where the number of representations is bounded, the set has to have zero density, right? So A has zero density. And if the density of A is zero, this implies that so this means A of x over x goes to zero. Suppose I let x equal to a sub n. Maybe this is a sneaky way to get what I want. So let x equal a sub n. So a of a sub n over a sub n, which is n over a sub n, because this is the counting function. This counts the number of terms of the sequence up to the nth term of the sequence. And that's n. This is n over a sub n. This goes to zero, or equivalently, an over n goes to infinity. So the useful fact I want to take from this is that if a set of integers has a bounded representation function, then an over n goes to infinity. Okay. Well, a set of integers whose representation function is eventually constant certainly has satisfies a of n over n goes to infinity. So let's see. I said I was going to use, or I said Erdős and Turan used the Fabry-Gap theorem. What does the Fabry-Gap theorem say? Oops, thank you. Oh, it's very useful. Fabry-Gap theorem. Suppose we have f of z is some power series, c sub n, z to the a sub n, summation, n goes from 0 to infinity. If this function f of z has radius of convergence 1, and if limit n goes to infinity, an over n is infinite, then the unit circle is the natural boundary of f of z. That is, you can't, every point on the unit circle is a singularity. You can't extend this analytic function to anywhere outside the unit circle. So that's the Fabry-Gap theorem. And so this is the Erdős-Turan theorem. Erdős-Turan theorem says the following: let A be a set of non-negative integers if R sub A2 of n is constant, let's say equal to C or equal to K, for all sufficiently large n, for all n equal to, or, all right, sorry. The statement is, this can't happen. So let me just write it as follows, so I don't have to erase too much. Let A be a set of non-negative integers. It is impossible that the representation function is bounded for all sufficiently large n. Okay, and the Erdős-Turan proof goes as follows: let f of z be the generating function, f sub a of z be the generating function of the sequence A, then f sub a squared of z is summation a in a, r sub a2 of n, sorry, not summation a in a, this is summation, sorry, oh, thank you, summation n goes from 0 to infinity, R sub A2 of n, z to the n. But from some point on, this representation function is constant. So there's some polynomial P0 of z, the initial terms of the sequence, plus from some point on, this R sub A2 of n is just equal to k. So this is equal to this polynomial P0 of z plus k z to the n naught over 1 minus z. So f sub a of z satisfies a certain polynomial equation. It's an algebraic function. And for an algebraic function, the unit circle is never the natural boundary. But if, if R sub 2 of n were equal to k, for k greater than or equal to k naught, then Fabry's gap theorem would tell us that the unit circle is the natural boundary, and it's not. So I apologize for saying this in a slightly convoluted way, because it really is extremely simple. So the argument is, suppose you had a set of non-negative integers for which the representation function, the twofold representation function, were eventually constant, then the sequence the sequence of integers is zero density, and an over n goes to infinity. But that means by the Fabry-Gauss theorem that this generating function would have the unit circle as its natural boundary. But this function satisfies this algebraic equation, and algebraic functions can be extended. They're never just restricted to the unit circle. So that's the proof of the theorem. So there are two remarks about this I would make. First is it does use some, fairly sophisticated result in complex variables. And Ehlers-Turan said there should be a simpler proof, but they couldn't think of it. Turns out there is a simpler proof. There was a famous physicist named Dirac. And at one point, he wasn't married. And someone, it might have been Wigner, said, you should just marry my sister. So he married his sister, who already had a child. And so Dirac had a stepson, George Dirac, who became a mathematician. And George Dirac made the following observation, which no doubt embarrassed Erdős and Turan completely. The observation is the following. You're looking at numbers that are, the representations of an integer is the sum of two terms from your sequence. Now, suppose you take the number 20. So if 10 is the number in your sequence, then one representation of 20 is 10 plus 10. And every other representation actually comes as a pair of representations. Like if you have 3 and 7, then you have n is 3 plus 7, and n is also 7 plus 3. So for every number a, which is in your sequence, the number of representations of 2a has to be odd. It's 1 plus some even number. But for every number that's not in your sequence, the number of representations is even, because there is no a plus a that's possible. And you have an infinite sequence, so there are infinitely many even numbers and infinitely many odd numbers. And it's therefore impossible that the representation function could be constant from some point on. So that was George Dirac's subsequent little paper in the Journal of the London Math Society, saying that these two truly great mathematicians missed a very elementary observation. Of course, you might say, well, maybe the theorem So, and the Dirac argument does not apply to a representation function which does not distinguish the representations 3 plus 7 and 7 plus 3. So if you look at representations where you count every representation really once, essentially once, you don't allow permutations of the summands, then maybe the Erdős-Turan result is true. And it is true, but they didn't prove it. They just stopped where they stopped. But you can actually take this Erdős-Turan method and apply it in a slightly more general situation, which covers the case I just said. And so here's, this is really just like a epsilon step beyond what Erdős and Turan proved. And keeping in mind that everything I've been saying was supposed to occupy just the first 5 minutes of my talk. Let me just skip a couple of things and state a slightly more what is the nice result to state? So I'll state this as a theorem, and I'll try to figure out what to say. And once I say it, I'll try to figure out if there's a proof. So there does not exist a set A of non-negative integers. And let's see, let's not restrict ourselves to h equal 2, so that h be any number greater than or equal to 2. Do I want to say that? Maybe just to be safe, because it's only a seminar, I'll just say that h equal 2. Should be true for any h. There does not exist a set of A non-negative integers such that the representation function, and let me just keep it as the strictly ordered representational function, R sub A H of n, is eventually periodic. So it doesn't have to be constant, it's say eventually periodic. So what this means is that, i.e., there exists an integer that's called L and n naught, such that for n greater than or equal to n naught, the number of representations of n as a sum of h elements of A depends just on the congruence class of n mod L. So I can say it like this. So summation L plus JL equals some number K sub L for all J greater than or equal to some J naught. So you're just taking the integers, dividing them up into the congruence classes modulo capital L, and in each of those congruence classes, if you hope that there might be a function for which the representation there might be a sequence A for which this representation function might be constant on the congruence class, that can never happen. That's impossible. And the proof is exactly the Erdős-Turan proof. So one considers the generating function of f sub A of z. We know that which always at a loss for the right subscripts. A sub t over t goes to infinity. So these exponents are growing fast. So by the Fabry-Gap theorem, this series certainly has a radius of convergence 1, and the unit disk would therefore have to be the natural boundary of the function. But if you take f sub a of z to the h, this is summation r sub ah of n, z to the n goes from 0 to infinity. So up until you get to some number, that you get some polynomial, p0 of z, plus you have summation, let's say j goes from j naught to infinity. So for an integer that's congruent to little l modulo big L.
One moment.
That's weird. That's my phone talking to me. So for integers in the congruence class little l plus j sub l plus little l mod big L, this is k sub l z to the l plus jl, right? And this is p0 of z plus, what is this? Summation, summation L goes from 0 to capital L minus 1 for each of the congruence classes. And you look at the z's and the z to this exponent, the numbers in that particular congruence class. This L goes from 0 to capital L minus 1. K sub L, z to the L over 1 minus z to the capital L. That's f sub a of z to the h. And again, this says that f sub a of z is an algebraic function. It doesn't have the unit circle as its natural boundary, so we get a contradiction. So you cannot have even eventually periodic representation of functions for a function. Here, just to make the argument simple, I was just using, again, the ordered representation function. But you can also deal with the representation function where you don't count 3 plus 7 and 7 plus 3 as different representations. So let's just look at the case h equal 2. So what would be a generating function for the unordered representation function? So here's if you take f of a of z squared, you're counting every representation by the order. 3 plus 7 is one representation of 10, 7 plus 3 is another. If you had 5 plus 5, that would occur here just once. 3 plus 7, 7, 3, that occurs twice. But if I add to this f sub a of z squared, here I'm just counting the representations of the form a plus a for an element a in the set. So this is just counting those special representations a plus a. If I add the two of these together, now I'm counting every representation twice, right? This counts the representations 3 plus 7 and 7 plus 3 twice. This plus this counts the representations 5 plus 5 twice. So just to make things nice and divide by 2, now what I have is the generating function for r sub a to, I'll call it prime of n, z to the n goes from 0 to infinity, where r sub a to prime of n is the number of ways you can write n as a1 plus a2, where a1, a2 are in a, and a1 is less than or equal to a2. So this is in some sense the more natural representation function. But then the argument, I hope, let's see, maybe it doesn't. I had thought that this would give me the right argument, because this again would be some polynomial plus from some point on, this is a constant k, k z to the n naught over 1 minus z. So, so here's a question for the complex variables, complex analysts among you. Does this imply that the function f of z is algebraic? So this means that, I mean, you clear the denominator, that's never a problem. But you have some polynomial, but the polynomial involves f of z squared, but not f of z, it's f of z squared. So is f sub a of z an algebraic function?
I mean, you can certainly find equations, slightly like this one where f is transcendental, right? If f satisfies f of z squared is equal to z is f of z minus z, right? Then f of z is going to be just z to the 2 to the n, which is sum of z to the 2 to the n, which is transcendental.
I was trying, so I had hoped that I could deal with the unordered representation function by exactly the same argument, but I had forgotten this little 2 is inside the parenthesis.
Yeah, you need to be a little clever there.
Yeah.
Nothing routine will work.
Right. Wow. Okay. And I'm trying to remember whether George Dirac in his paper had not only given the one-line proof that the representation function in the ordered representation function definition cannot be eventually periodic, but also in this case. And I have to look up Dirac's paper. I just don't remember what is in it. Okay. All right. So again, what brought this to mind was that David had asked me about this paper of Erdős and Turan, and I hadn't looked at it for a long time. But this is the proof. This was the proof. It's a very pretty proof, but using a sledgehammer to squat a fly. Okay. So this was my introductory 5 minutes, and let me just use my last 5 minutes to say what I was going to talk about. So it has to do with oscillations in number theory, in additive number theory. Actually, before I go on, what is probably the most important part of this Erdős-Turan paper of 1941 is the last paragraph. In the last paragraph, they make a conjecture, ask a question, and it's the following. So this is one of the two statements that are called Erdős-Turan conjectures, out of many, but the two really famous ones. And the one out of number theory says the following. If A is an asymptotic basis of order 2, then the representation function, no matter which representation function you pick, is unbounded. So they proved it cannot be eventually constant. At least in the ordered case. And I just showed that it can't be eventually periodic in the ordered case. In both of those cases, the representation function is bounded. And their conjecture is the much stronger statement that the representation function cannot be bounded. It can't be that it's bounded, but has some highly erratic behavior. It simply cannot be bounded. This is really a very, very famous result. And when I was a graduate student, I thought I would solve this conjecture and failed. But I had the idea that one natural place to study this would be, so this says that, what does this conjecture say? You have an asymptotic basis of order 2. That means you have a set of integers, and every number from some point on is a sum of 2 terms of the sequence. Now, and you want to show the representation function can't be bounded. Well, suppose you have some, what you might call superfluous numbers in your set A. Like suppose you have this set A, it's an asymptotic basis of order 2, but you could throw away some elements of the set, and it still is an asymptotic basis of order 2. So that just reduces the size of your representation function. Any number that uses a summand that is one you threw out will be destroyed. So in some sense, if you want to study this conjecture, you might want to look for asymptotic bases of order 2 that were minimal in the sense that no subset was an asymptotic basis of order 2. There is nothing you can throw away. And now that's a little bit tricky as a definition. In many cases, it's easier to prove that if you have some arithmetically or combinatorially defined object, you can find a subset that's minimal. But in this case, what minimal means is if you were to delete any element of the set, it's not that you might fail to represent some other number. That would be okay. Because an asymptotic basis allows you to fail to represent any finite number of elements. So you can imagine that you have a set where you could throw away any element and it still is a basis. And you could throw away another element and it still is a basis. So even the question of the existence of these minimal asymptotic bases isn't so trivial. So let's just say that an asymptotic basis is minimal. So asymptotic basis of order H, we're not changing the order, is minimal. Asymptotic basis A, order H is minimal if A with A naught removed is not an asymptotic basis of order H, no matter what A naught you pick for all A naught and A. So you say you have a minimal asymptotic basis. This means if set A is a basis of order H, every number from some point on is a sum of H elements from the set. But if you throw away any element at all, not just some very special one, any randomly chosen element at all, you lose this asymptotic basis property. So somehow every single element in the set is responsible for and essential for the representation of infinitely many different numbers. So such a sequence would be called minimal. And it's not obvious that they exist, but they do exist. And there are a lot of questions about these things. Minimal bases exist, but you can also ask, does every basis, in fact, contain a minimal basis? And the answer to that question is no. In fact, there's a very nice result. This was due to Erdős and me from a long time ago. There exists an asymptotic basis A such that A with S removed is an asymptotic basis of the same order if and only if S is finite. So this was actually rather surprising. So you had this set, which has this, it's an asymptotic, but let's just look at order two. Every element from some point on is a sum of two elements from the sequence. If you throw away any finite set, no matter how large, it still has this property. You may lose the representation of finitely many numbers, but from some point on, every integer is a sum of two elements from what's left. But if you
Do you
throw
have it?
what?
Do you have a sense? Do you have a sense for what's generic? That is to say, are bases like this generic, or does a typical basis in some sense have a minimal basis inside it? I'm not asking a precise question. I'm just asking for a
Right,
sense
right.
of.
I do not know. I don't know. I don't know. But this is
My intuition would have been that this situation that you're describing is actually generic. That most bases, in some sense or another, you can just keep taking out elements and it'll still be an asymptotic basis.
right. You might be right, but no, and I mean, and I understand the intuition, but I just don't know.
Well, you'd need to define the question first, and I haven't done that.
Yeah. So there's a case where I prove that almost all sets of a certain size have a certain property, and Kevin O'Brien and a colleague of his proved that almost all sets don't have that property. And how is that possible? It's because we use different probability measures. And both of them were natural, but you had diametrically opposite results. Here, you have this set with the property that you can delete any finite subset, but no infinite set. And the combinatorial principle that there's no maximal finite subset of an infinite set says that this basis A cannot contain a minimal basis. But what the generic case might be, that really is a very nice question. But I don't know. So, and I'm not used to, I'm not comfortable thinking about things in that way. When I was working with Erdős, he did almost everything probabilistically. And I spent a lot of time when we had some more or less probabilistic argument, getting rid of the probability and proving things combinatorially. I just don't have a emotional connection to probability arguments. So, but the answer, but your question is very nice, but I have no idea what the answer might be. And I can't think offhand. I mean, sort of the obvious way to try and prove a statement like that is to use this Erdős-Renyi probability construction on the set of sets of natural numbers. And I've, proven theorems that are sort of probabilistic that use this Erdős-Renyi method, but I always feel that I failed somehow if I have to use probability to prove a theorem. The ergodic theory people think differently. But anyway, okay, that's it. My time is up.
Well, just one quickie. Did you manage to prove that for minimal bases, anything holds? The Erdős conjecture.
No, in fact, I'll tell you a story about this. So I spent, when I was a research student, I spent a year in Cambridge. This was a long time ago. And then I wanted, but I didn't have to be back in the States till September, of course. So I traveled in Europe a bit. And then I went to Israel, and I just wanted a place where I could sit down and work. So I went to Mahon Weizmann. I went to the Weizmann Institute in Rehovot, and I walked in, and I found the math department. And I said, I'm a graduate student in math. I want to, I just want to be here for the summer, use your library and work. So there's only one mathematician there that summer, and that was Shlomo Sternberg. And they sent me to Shlomo, and Shlomo said, what is it that you're interested in? And I told him, and he said, no one in Israel is interested in this, so you might as well stay here. So, and what they had there was the book of Halberstam and Roth on additive number theory, which I studied a lot. And that's where I came up with this idea of minimal bases. And I could prove lots of theorems about them, in particular that they existed, and all of which were new. But when I looked at the representation function of these minimal bases, it had the kind of behavior that you would expect if your idea were going to fail. Namely, it would go for like huge distances where the number of representations was very small. And then there would be like this jump. And then it would be very small for a long time. And there would be another, maybe a little bit bigger jump. So if you looked at sort of like the spectrum, like this representation function, it was really bounded almost everywhere. But then you had these peaks, and the existence of the peaks, it tells you you have no chance of, at least you haven't proved the Erdős-Turan conjecture. Now, about 30 years later, I was back in Weizmann to give a talk, and I was curious, and I went to the library, and I pulled out the copy of Halberstam and Roth that I had been studying that summer. And, it's an old library book. So these were the books where when you take out the book, you write your name on like a 3x5 card that you put it on the desk. And so I looked at the book, and in 30 years, I was the last person to have taken the book out. It's just, yeah. So anyway, no, these minimal bases are very interesting. I'm going to talk a little bit about something, because there's also a dual notion. Because if you have a basis, that means every number from some point on is the sum of, let's say, two terms from the sequence. If it's not a basis, that means infinitely many numbers are not sums of two terms from the sequence. And if you have so let's call that a non-basis. And just the way you can consider minimal bases, you can consider maximal non-bases. And there are certain oscillation properties between bases and non-bases that are very interesting. That's what's supposed to be in this book that Springer's been waiting 10 years for. And somehow I promised it to them. They told me I have to have it in by January. They thought they were being generous enough. But anyway, okay, that's it. Let me somehow get out of this video business here. Stop video, FaceTime camera. There we are. Okay.
Okay.
Where's my?
Nice talk, Mel.
Oh, thank you. How are you doing?
Thank you, Mel.
Yeah,
Thank
yeah,
you,
well,
Dave.
thank you. Thank you.
Could probably
by the
stop
way-
recording at this point.
Sorry?
You could probably stop recording at this point.
Oh, I should have. Thank you.